Now that we've done some theoretical work with the definite integral, let's see how it works in practice with some simple examples. For example, in this first example, if I'm asked to find the definite integral from 1 to 3 of 2x plus 3 square root dx, first of all, I understand that this is the area under the curve, and I'm going to integrate this. Well, I first have to understand that this can be written as the integral from 1 to 3 of 2x plus 3 to the 1/2 dx. Now I see this is like an integral of ax plus b to the n. Well, I just have to apply my rule for that. I know that'll be 2x plus 3 to the 1/2 plus 1, which is 2 over 2, which will give us 1/2, or 3 over 2, divided by 3 over 2 times the coefficient of x, which is a, in this case 2, and I'm going to evaluate that all. The 2's will cancel. I get 2x plus 3 divided by 3, and I'm evaluating that from, and this is to the 3 over 2 power, and I'm evaluating that from 1 to 3, which means I have to plug in 3. When I plug in 3, I get 3 times 2 is 6, plus 3 is 9. If I take the square root of 9, I get 3, and cube it, I'll have 27 over 3, which is 9. If I plug in the 1, I get minus the square root of 125 over 3. You can do the math slowly, and you'll see if you plug in the 1, that's what you do get, which comes out to, when you work on your calculator, 5.27. And that, again, represents the area under the curve from 1 to 3. Here's another type of problem you might encounter when dealing with definite integrals. In this case, they've given us the lower bound a of 0, and the upper bound is no longer b, but it's m. And they say find m. And they tell us that the answer, or the area under the curve, is -4. So we have to integrate this. Well, if we integrate this, we're going to get 2x squared divided by 2 minus 4, x to the 0 goes x to the 1, and we're evaluating that from 0 to m, and we're told that the area, or the answer, is -4. Well, if that's the case, we can substitute in m. First, our 2's will cancel, and we'll get m squared minus 4m. If we substitute in a 0, we get 0 minus 0, so it's going to be minus 0 is equal to -4. So now we can just solve for m. When dealing with m squareds and m in the same equation, the method is to get everything on one side. M squared minus 4m plus 4 equals 0. If I add 4 to both sides, that's my resulting trinomial. And then I can try to factor this. Well, m, minus 2, and minus 2 gives me m minus 2 squared. Therefore, if m minus 2 equals 0, then, therefore, m is equal to 2 when I solve that equation. So I'm really evaluating from 0 to 2, and that's what I get. When evaluating the definite integral, here's a third type of problem you may come across. Suppose that f of x and g of x are continuous functions over the interval from x is equal to 1 to x is equal to 5, and that 1 to 3 f of x dx is -2, and 1 to 3 g of x dx is equal to 3. They've given us the area under the curve for each of those functions. Evaluate 1 to 3 f of x minus g of x dx. Well, we can separate this out using our rules from 1 to 3 of f of x dx. And with our rules, we can pull the constant out, minus 1 to 3 g of x dx. And now we can substitute. We know 1 to 3 f of x dx is -2, so it becomes 3 times -2 minus, and we know 1 to 3 g of x dx is 3. So this will give us -6 minus 3, which is -9.